Welcome back, students. The next topic is inverse functions. Let's have a very brief review on implicit differentiation. We start from an implicit relation, kind of like these, or that, and take the derivative implicitly regarding x as independent variable and y as a dependent variable or function of x, kind of like this. Derivative of x cubed, well, 3x squared. And product rule here, derivative of x is 1, but derivative of y is y prime. And finally, y cubed, we take the derivative by y, so 3y squared, and y prime popped out. This kind of thing, that's implicit differentiation. And we can use implicit differentiation technique to inverse functions. Well, here we go. Derivative of inverse function is, well, more or less reciprocal. But in theory, in practice, this is theory, but practice is kind of like this. Y equals to f of x, and no, we are looking for inverse function, right? Inverse function. This one is equivalent to fy is equal to x, isn't it? And then here we take the derivative implicitly. Then what happens? By chain rule we have f prime of y, and then the derivative of the inside, y prime, is equal to the derivative of the right hand side, that's just 1. And then finally we get this. Y prime is equal to 1 over f prime of y, and basically what we see is over there. In the end, we'll have to re-express the denominator in terms of x, and that can be a little bit of an agonizing step, and we'll have to do this for a couple of functions, but in the end, that's all there is. It's an application of implicit differentiation. Alright, let's go with the first example, that is logarithmic function. Here is a derivative of log function, and derivative of log is 1 over x, and then if you have a composite function, this is basically 1 over u of x, and then by chain rule we multiply the derivative of inside. Oops. And then if you simplify this expression, what do you get? We have u prime over u. So it's going to be better if you take this as the entire formula and then remember it. For arbitrary base, I don't like to use arbitrary bases, but well, here they are. Now, how do you prove that? Well, here's the proof. We begin with y equals to log of x, and it is equivalent to e to the y is equal to x. And then we take the derivative implicitly. Exponentials stay the same, and then by chain rule we have dy dx, and right hand side the derivative is just 1. And solve with respect to dy dx, and this is what we get, 1 over e to the y power, and e to the y power is x, so we have 1 over x. In the end, we get this. Another example. Okay, let's go to inverse trigonometric function. And here are some interesting formulae. Arc sine is 1 over 1 minus x squared in square root. That's important. Arc cosine is not that important. Arc tangent, that's important too, even more important. And the others, no, not really. Arc secant sometimes shows up, but only sometimes. Among these, only important things, in my opinion, are arcsine, moderately important, and arctangent, this is a little bit more important, but still moderately important. How do we deduce those? Well, the same thing. Y equals to arcsine of x is equivalent to sine of y is equal to x, isn't it? And then you take the derivative implicitly. Cosine of y, and by chain rule we multiply y prime, and the right hand side derivative of x is 1. So what is y prime? It is 1 over cosine of y, but that's not the end of the story. This is correct derivative, yes, but it's y expression. We have to express it in terms of x, and there comes a bit of a strange step, cosine squared of y, and then we apply Pythagorean identity, 1 minus sine squared of x, squared of y, excuse me, and remember sine of y is x, so 1 over square root of 1 minus x squared, because you see sine of y is x. This is a bit too long. No, this is okay. This is okay. So this is a derivation. We just start and then write it as without the inverse, and then take the derivative implicitly. I said this was a little bit important too, so let's talk about that one too. Again, as briefly as possible. Let's say y is inverse tangent of x, and that's equivalent to tangent of y is equal to x. Here we take the derivative implicitly, so derivative of tangent is secant squared, and then times y prime is equal to derivative of x with respect as 1. So we have y prime is 1 over secant squared of y. And we apply Pythagorean formula as before. What is secant squared? Is 1 plus tangent squared. Oops, this should be plus, excuse me. And finally, what is tangent of y? That's x. So we get this 1 over 1 plus x squared. The other derivations, I'll leave those to you. And of course, if you do not remember these derivations, or if you cannot follow, just memorize them. Here's one moderately important formula. Here's another moderate important formula. The others, not very important. Now let's go to some application problems. Applications of logarithmic functions. Find out the derivatives of the given function. Okay, here we go. What is y prime here? Let's apply the derivative rule for the log function. 1 over whatever inside. And by chain rule, you have to multiply the derivative of the inside, 2x plus 2. But then again, if you multiply, you're multiplying to the denominator. You're multiplying to the numerator, excuse me. So in the end, what do you get? You get 2x plus 2 over x squared plus 2x plus 3. Many students go from here all the way to here directly. Well, we have very same expression there as a solution. Okay, how about the next example? Well, we have log function, but looks like we have to use a product rule. No big deal. Just apply the product rule. Derivative of the first function and the second function plus first function times the derivative of the second function. Simplify a little bit, and that's it. X squared times 1 over x. So here we go. 2x log of x plus x. How about some applications of inverse trigonometric functions? Well, let's see. This one, the first problem. Okay, let's do that. Shouldn't be too bad. By chain rule, we apply the derivative of the outer function. Inside never changes. And then we multiply the derivative of the inside. What is the derivative of the inside? You just have to remember the derivative formula for arctangent function. And that's it. I don't think you have to simplify this thing any longer, but it is possible to do that. I think in my answer key I did. How about the next problem here? Is this really worthy? No, not really, particularly considering that we already did arctangent. So let's do this one. Arcsine and square root of sine. Let's see, f prime of x. How does that thing work? And outer function first. 1 over square root of 1 minus. That's it, isn't it? And then what's inside? We have square root of sine of x. Okay, that is the derivative of the outer function. Next, we have to take the derivative of the inside by the chain rule. Okay, let's just do it one step at a time. 1/2 inside never changes. Subtracting 1 from the power. Now, derivative of the all the way inside, that's cosine of x. Do we need to simplify this thing? No, I don't think so, but let's do just one more simplification, because square root of square, so we just have sine squared of x over here. Let's do just that and then nothing more. You see, square root of square cancel each other out, and this is what I got. In my answer key here, I simplified a little bit further, as you can see here. So much for inverse functions. In the next video, we're going to talk about logarithmic differentiation.